Hello students, this is lecture 9 of MTH 201. In the last lecture we discussed about limits and continuity. In today's lecture we will talk about differentiability of a function. So let us first look at these two pictures and let us focus on the first one. We are going to define tangent plane to a graph. So suppose you have a function of two variables whose graph z equal to f of x comma y, which is this curved thing, curved surface that you see here. That's the um, graph of the function. Okay. Now suppose I take a point x naught y naught in the xy plane and you look at its image on the graph. So you get a point x naught y naught and the z coordinate is given by f of x naught y naught, right? We want to define tangent plane to this graph at this point. So you already have these notions of tangent lines to a graph, which is a function of one variable, right? Graph coming from a function of one variable. We already know that idea. Now we are going to extend that idea to more than two variables. We are going to, more than one variable. We are going to talk about that notion for functions of two variables. So the graph that you get is in three variables and this is how it looks like, and we want to define a tangent plane to this graph at this point. Okay. So last time we saw two things. So if you look at this curve, okay, this horizontal curve on this graph, where your y coordinate is fixed and it is equal to y naught. So you look at all the points on the graph where y is equal to y naught. So it's basically f of x comma y naught. So you get a curve, right? Because y coordinate is fixed. Now at this point x naught y naught, you look at the tangent line to this curve. Its slope is nothing but the partial derivative of f with respect to x at the point x naught y naught. Right? This we saw last time. Similarly, when you fix the x coordinate to be x naught and you vary the y coordinate, you get this other curve, right? Now this curve has slope. So if you look at the tangent line to this curve at the given point x naught y naught, then the slope is given by the partial derivative of f with respect to y at the point x naught y naught. So already for two curves on this graph, you know the slopes, and we are going to use this fact. Okay. So now let us take the equation of the plane at the point x naught y naught f x naught y naught to be like this. Z equal to fx naught y naught plus a times x minus x naught plus b times y minus y naught. Now you will wonder how we get this equation. Okay, so let us look at it differently. Okay, suppose you bring this z on this side. So what do you get? You get minus of z minus fx naught y naught plus a times x minus x naught plus b times y minus y naught equal to 0. So general equation of a plane which passes through such a point is a times x naught minus x naught plus b times y minus y naught plus c times z minus fx naught y naught. Now the c coordinate is the component of the normal vector in the z direction, right? Now we are assuming here that there is a non-zero component in the z direction. So if there is a non-zero c, which is the non-component in the z direction, you can divide the whole equation by c, right? And therefore, this coefficient of z becomes 1 or minus 1. So now think about it. When is the z component going to be 0? Z component is going to be 0 if the plane is parallel to the z axis, right? Now think about it. Can you have a function whose graph, when you look at its graph and you take a point on the graph and you look at the tangent plane, it is parallel to the z axis? That's not possible. Okay, so therefore we only talk about situations where you get a plane which is not like that. Okay, so let me go to the picture again. So all the planes that you see on this graph are going to be such that they have some z component, otherwise they will be vertical planes, right? And you can imagine how your graph should be if your plane is vertical. Okay, so I would like you to avoid the end points, the boundary points, so that you are completely inside the graph, you are not on the boundary. Okay, so this issue we will again take up in the live session, but for now let us assume that planes are non-vertical. So there is a non-zero k component and hence you can write equation like this. Okay, so let me call this right hand side to be gxy. Now these next 2 points we already discussed while discussing the second picture on the previous slide. So we saw in lecture 7 that fx, x naught y naught, which is the partial derivative of f with respect to x at the point x naught y naught, is the slope of the tangent line to the curve z equal to f of x comma y naught. So y coordinate is fixed, which lies on the graph of this function at this point, right? Similarly, we saw that fy, x naught y naught, is the slope of the tangent line to the curve f x naught comma y. So x coordinate is fixed, lying on the graph of this function at this point, right? So you have those two slopes. Therefore, if this plane is tangent to the graph of the function at this point, then the slopes of the corresponding curves on the graph and in the plane should match, right? Because those tangent lines should also be contained in where? They should be contained in the tangent plane, right? At this point. And therefore, if you take the partial derivative of this plane with respect to x at the given point, which is nothing but a in this case, should also be equal to the slope of that line, right? Which is fx at x naught y naught. Similarly, when you take the partial derivative with respect to y of g, which is b in this case, that should be equal to the partial derivative of f with respect to y at this point. So therefore, your tangent plane, this plane becomes this, right? I have just substituted a to be f sub x and b to be f sub y. Now this can also be rewritten as, now you bring all these quantities to the left, you get minus of fx x naught y naught times x minus x naught, this term, then this term, plus z minus f of x naught y naught equal to 0. Now if this is the equation of the plane, then what are the normal? So this is what we have. Let f be a function of two variables x and y. The tangent plane to the graph at the point x naught y naught has normal. So normal are the coefficients of x minus x naught, y minus y naught, z minus f of x naught y naught, which is this, and equation is given by this, right? Now, of course, this tangent plane is defined only when both the partial derivatives fx and fy at x naught y naught are defined. Okay, so this is how the picture of a tangent plane looks like. So let us look at an example. So find the tangent plane to the graph of the function fxy equal to 1 by x times y at the point 1 comma 1. So for this we need to compute the partial derivatives, which are this, and if you compute them at the point 1 comma 1, they become this, and also you need the value of the function at the point 1 comma 1, which is 1 in this case. So putting it in the equation of the tangent plane, which is z equal to f x naught y naught plus partial derivative of f with respect to x times x minus x naught plus partial with respect to y minus y naught. So z remains as is, f of 1 comma 1 is 1, fx of x naught y naught is minus 1, so minus sign, x naught is 1, then fy x naught y naught is minus 1, so you get minus sign, and y minus y naught, so y naught is 1. So this is the equation that you get, and you can simplify it. I have not simplified it so that you see how it comes out, but it comes out to be x plus y plus z equal to 3, right? Okay. So in this example, fx and fy are only defined at the points x naught, y naught, where both are non-zero, right? In fact, that is the domain of the function. When either x or y is 0, function is not defined. So this function is only defined on points where both x and y are non-zero, right? And at all those points you have an equation of a tangent plane, right? So now let us use this idea of a tangent plane to linearly approximate a function. Okay, so this is something that is not alien to you. So recall from one variable case that the tangent line y equal to fx naught plus f prime x naught times x minus x naught passing through the point x naught comma fx naught with slope f prime x naught is close to the graph of f near x naught, right? That is, fx naught plus f prime x naught times x minus x naught is a good approximation to the function fx for values of x near x naught. So close to x naught, this tangent line, right? This is the tangent line. This is close to the graph of the function, right? Similarly, it happens in higher dimensions. We will see it in a minute. But also, since f prime x naught, if it exists, it's equal to this limit, right? So now let us bring this term on this side. You get fx minus fx naught minus f prime x naught times x minus x naught divided by x minus x naught. If you consider this limit, that can be broken into two terms. First is this term and second is this term. But in this term, because you have limit x going to x naught, x minus x naught can be cancelled. Because when you talk about limits, x is not equal to x naught. X is approaching x naught, right? So you're just left with f prime x naught, but this difference is 0. So therefore, differentiability of f at the point x naught can also be expressed as existence of a number L such that, so instead of equality of these two numbers, think of differentiability as this limit being 0. And L is nothing but the derivative. So this is the notation. So instead of saying that f is differentiable at x naught if this limit exists, you rewrite it as existence of a number L such that this limit is 0. So these are similar notions, right? They are equivalent notions. So we are going to use the second expression for functions of more than two variables. It turns out to be more useful. Okay, so let us now extend this idea to functions of two variables. So suppose you have a function f from R2 to R, which is a function of two variables x and y. This is the definition. We say that f is differentiable at the point x0, y0 if the partial derivatives exist at that point and if this limit is 0. Let us read this limit. So it is fxy minus fx0 y0 minus partial of f with respect to x at the given point times x minus x0 minus partial of f with respect to y, y minus y0, right? Divided by square root of sums of these squares. Now denominator is nothing but the distance between, the Euclidean distance between the points x comma y and x0 comma y0, right? And then you will take limit xy going to x0 y0. Now if you look at this term right here, this term is nothing but the right hand side of the tangent equation of tangent plane, right? And this term is called the linear approximation of the function f near x0, y0. It's the same idea as linear approximation of a function of one variable, right? Where you take the right hand side of the tangent line. Now you are taking right hand side of the tangent plane. Few notes. First, this is the equation of the tangent plane, right? So this right hand side except the z term is called the linear approximation. And if you look at these last two terms in this limit, it can be written in matrix form. I am ignoring the negative sign. You can write it as the multiplication of this row vector fx fy with column vector x minus x0 y minus y0, right? So if you multiply, you get fx times x minus x0, which is this term, plus fy times y minus y0, which is this term. And this representation in terms of matrices is going to be useful later. So now we are going to extend the notion of differentiability from functions of one variable, from functions of two variables to now general functions. Okay. So let us now extend the notion of differentiability to a function f, whose domain is a subset of Rn. So now the function is on Rn and it goes to Rm. Okay. So let f1 through fn go from U, which is a subset of Rn, to R, and these are m functions on n variables, right? And let me call those variables to be x1 through xn. Let f going from U to Rm, a vector valued function. It's called vector valued because its range is a vector. And let it be defined as fx equal to f1x comma f2x and so on up till fnx, where x is a point in U which is in Rn, right? So it has n coordinates. So you have this. Then f is a function of n variables, x1 through xn. So this bold x is the tuple x1 through xn in Rn. And these functions f1, f2, so on up till fm, they are called its components of f. Now, so you have all these functions, right? So each fi is a function of n variables. So you can talk about its partial derivatives with respect to each variable, right? So suppose you're given a point x naught in U and you compute all these partial derivatives. So for each fi, where I goes from 1 through m, you have n partial derivatives with respect to each of the variables x1 through xn, right? So suppose all these partial derivatives exist at a given point x naught in U. Then you can define what is called a derivative matrix of the function at the given point, and it is not difficult to remember. Its size is m cross n. So m is the dimension of the range, so that is the number of components, and n is the dimension of the domain. So it is same as what you have seen in linear algebra. So if you take a linear transformation from Rn to Rm, the size of the matrix is m cross n, right? So it's the same thing. Now what is the first row? First row is all the partial derivatives of f1 at the given point. Second row is all the partial derivatives of f2 at the given point. And the mth row is all the partial derivatives of fm at the given point. So it's not difficult to remember. But for this matrix to make sense, you need all these entries to make sense, which is you need all these partial derivatives to exist. Okay, so this is called derivative matrix. Now, let us talk about differentiability of such a function at the given point. So we say that a function f from Rn to Rm is said to be differentiable at x naught if, first of all the partial derivatives exist at the given point, and when you look at the limit x going to x naught, fx minus fx naught minus the derivative matrix times x minus x naught divided by the distance between x and x naught, this limit should go to 0, where x naught is a point in Rn, so it has n components. I am indexing them like this, and the denominator, which is the distance between x and x naught in Rn, is square root of sums of squares of the individual differences, component wise or coordinate wise differences. Okay. Now, let us spend a little bit more time on this thing. So, suppose you focus on the numerator. Now, numerator, you should read it like this. So, fx has fx is equal to f1x, f2x, fnx. Write it as a column. Okay. Similarly, fx naught is f1x naught, so on up till fmx naught. Think of it as a column vector. Minus, we noted on the previous slide, dfx naught is this matrix which is of size m by n. And then x minus x naught, you write it as a column. So x is x1 through xn, x naught is x naught 1 through x naught n. If you take difference of these two points, you get coordinate wise differences, right? So this is what you get. So if you multiply these two matrices, you get a matrix of, you get a column of size. So this is m cross n, this is n cross 1, so it will be m cross 1, right? So this is consistent, right? All three matrices will be m cross 1. And if you multiply these two matrices, you get these terms, right? So when you look at these terms, you are taking this 1 term with this term plus 1 term with the second term and so on. So this is what you get. Okay, so I would like you to spend couple of minutes on this slide just to be sure about all the notations. Now the function Lx equal to this term, right, which is fx naught plus dfx naught x minus x naught, is known as the linear approximation of f at x naught. So it's the same idea as before. For a general point x in U, the derivative matrix dfx, if it exists, if all the entries exist, it's known as the Jacobian matrix. So instead of computing these at x naught, you leave it as in terms of variables x1 through xn. Okay, then it's known as Jacobian matrix. So let us look at this example to make things more clear. So you are given a function from R3 to R2, right? 3 variables to 2 variables. You have to compute, find the linear approximation and the derivative matrix at the given point. So let us first compute the components of this function. So first, it has first component, which is x plus z plus e to the y, and the second component is x cube. So you can compute all the partial derivatives of f1, f2 with respect to x, y, z. Okay, so you get all these 6 partial derivatives. You compute it at the point 1 minus 1 0. You get this. So I'm not spending too much time on these values. They are just obtained by substituting x to be 1, y to be minus 1 and z to be 0. And also at the given point, the function value is this, right? It has 2 components. So the Jacobian matrix is given by, remember the size of the matrix is 2 cross 1, I'm sorry, 2 cross 3, right? 2 is the range, 3 is the domain, 2 cross 3. First row is the partial derivatives of f1, the first component with respect to x, y, z. And second row is the partial derivatives of second component with respect to x, y, z. And if you set x equal to 1, y equal to minus 1 and z equal to 0, you get this matrix, right? So this is the Jacobian matrix, which is in terms of x, y, z, and this is the derivative matrix at the given point, which is 1 minus 1 0. Now what is the linear approximation? It's given by the value of f at the given point plus the derivative matrix times x minus the first component of the given point, which is x minus 1, y plus 1 and z minus 0, which is z. So you can substitute f1 minus 1 0 as a column plus the matrix times this, and you can multiply all these to get a column matrix, and that will be the linear approximation. Okay, so you should be very careful with the size of the matrix. So it is like what you have seen for linear transformations. Okay, it's the same thing. Okay. Now the question is, what is the relationship between continuity, partial derivatives and differentiability? You know all these 3 notions. So suppose you have a function f from U, which is a subset of Rn to Rm. It's a function with components f1 through fn, which are from U to R. If f is differentiable at a point, then it's also continuous at a point. So in one variable case, you know this fact, right? That a differentiable function is also continuous. But it's also true in with the definition that we have studied today. So this will be discussed in the tutorial. Another statement which I will just state here without proof, it's a big result, it's very important, and it says that if all the partial derivatives exist, that means if the derivative matrix is defined at the point x naught and all the partial derivatives are continuous. So partial derivatives exist and they are also continuous, then your function is differentiable at x naught. So remember, when we define differentiability, The first criteria, first hypothesis condition was that your partial derivatives should exist, and second was that limit thing, right? So here we are saying that just existence of partial derivative may not guarantee differentiability, but if they are also continuous at the given point, then your function is differentiable at the given point. Now this is the definition of continuously differentiable or C1 or smooth functions. So if all the partial derivatives exist and are continuous at all points of u, then we say that f is continuously differentiable or C1 or smooth. And by the previous bullet, if you have a C1 function, then all its partial derivatives exist and are continuous, and therefore function has to be differentiable. So this is the flow chart. If partial derivatives exist and are continuous, that implies differentiability. And of course, differentiability requires all the partial derivatives to exist, right? So this implication is from the definition. Okay, but just existence of partial derivative need not imply differentiability. You will see an example in the problem set. So partial derivatives existence is not enough to guarantee differentiability. In fact, it does not even guarantee continuity. Forget about differentiability. So if it can't guarantee continuity, then it can't have differentiability, because differentiability implies continuity. So you will see an example that converse does not hold true. Okay. So let us conclude this lecture with this example. So let fx by be x by y plus y by x for all x and y whose product is non-zero, right? Then only this function is defined. Then the partial derivatives are this. You can compute. Both of these exist and are continuous at all the points in the domain, right? You can see that. And hence f is a C1 function on its domain, which is all the points of x and y in R, all the points of R2 such that x times y is non-zero. And therefore, because the function is C1, it is differentiable at all the points, right, by the previous slide. So let us stop here.